Good Monday morning. Sorry, good Monday afternoon, everyone. Welcome to Maths for Construction. Today, I just want to take a review of logarithms because we saw the derivative of a log function, right? So a logarithm is an index or power or exponent that's really what it is. A logarithm is just another word for index or power exponent, right? So review some things. This might be a long lecture today. There's plenty talking. Indices. So review our indices, right? Say 2 to the power 3 is equal to 8, right? There's a familiar equation, right? 3 is the power, right? 3 is the power or index or exponent, right? You have lots of synonyms for that. 2 is the base, right? 8 is the final. 8 is the final answer, right? So historically in mathematics, we when people are solving equations, they usually come up when I solving equations, they solving real world problems, and it turns out that you might have to learn some mathematics in order to solve a problem. So like many hundreds of years ago, human beings had to solve something like this, but they didn't have the language of mathematics in order to write this down, at least not all cultures, right? But like, what's a real world example of this, right? You have some money, you had some money and I give you $5 and now you had $12. How much money you had before? What plus 5 is 12? You know what I mean? There's a linear equation, right? We had to invent basic arithmetic in order to solve things like this, okay? And at some point in time, you know, the idea debt came along, DEBT, right? Being in debt, okay? So 12 plus X is equal to 7. And, you know, yeah, somebody, okay, I had $12 before, and then I added some debt, and now I have $7. How did this happen? Positive numbers don't work like this. You don't add a positive number to 12 and get a smaller number. So many hundreds of years ago, human beings had to invent the concept of negative numbers. That was a stretch, you know, at the time. And they used to say, you know, negative numbers is the devil, you know, is heresy, is Satan doing its work, you know what I mean? Because it advanced and it peculiar and it weird. So people is like, oh my gosh, you know, they stone you down with a Bible if you're talking about negative numbers. But this is another equation we had to solve, and the solution is a negative number. And then, you know, the years went by and, you know, people had ideas about, you know, things compounding on each other and multiplying and things being divided and so on, right? And then, you know, at some point, people had to solve equations like this. Again, you didn't have mathematics, they deal with it with a real world problem. You know, I have an amount of money that was squared. And when I add 3 to it, what is 7? So this involved finding the square root. So again, mathematics had to change. We had to invent new capabilities. Like, what's the idea of a square root or a surd? This is easy, right? This is 2. The answer is 2. So coming up with square root something, again, that's more devil work, right? The actor Satan, these square root symbols, like, well, what is that? You know? Then you had things that it wasn't a fraction. You couldn't represent it exactly as a fraction. Like, you know, if you had to solve this equation here, right? How, you know, what number when you square it and add 2 is give 7? That's not a nice looking number, it's the square root of 5, right? What's the square root of 5? You can't represent that as a fraction. So all the knowledge we had about fractions went out the window. This is a irrational number. So again, mathematics had to deal with more devil worship and Satan and burn it at the cross and all these things, right? Oh, these numbers, this is the work of Satan, right? Well, what do you need this for? What's this for? Why that useful, you know? Throughout time, human beings always have to solve some kind of equation, right? Yeah, now, all these equations here, the unknown is in the base, right? The base is the number that you see here, not the power, right? So you could think of 8 as a base and 2 as a base, but 3 is not a base. So all these equations involve a base to some power. The unknown is the base, right? So the unknown is the base raised to some power. Like this equation, yeah. So for example, this equation. So mathematics matured at some point where humans began solving problems where the unknown was a power. So they would say something like, you know, 3 to some power x is equal to 9. Okay. What is x? They can't just divide by 3, right? That's not gonna work, right? This is a different kind of mathematics happening here. And originally, again, it was the work of Satan, right? Because who need that? Why are you gonna write this what is looking so evil, right? 3 to some power is 9. Now we know that the answer is 2, but how you just get that, right? What if I say, you know, well, 3 to some power is 10? You can't just divide 10 by 3. 3 to the power 3.33 is not 10, you know, like what is happening here? And this is where we had to shift. We had to shift the equation, the form of the equation, right? So the above equation is called the exponential form. Why is it called that? So the power is an exponent, right? X is a exponent. Remember, exponent is a synonym for power or index, right? Indices is plural. It means more than one. Index, it means one. Exponent is a very famous term for that. So this is the exponent form of the equation. 3 to some power is 10. There's not surds or roots or anything happening here. There's something different. So then it became useful to represent so these exponential equations, we want to represent it in a form where the unknown is a base, not a power. So what does this say? This says x is the power that 3 must be raised to give 10. So how do you read the equation? 3 to the power x is 10. All right, that's how you read it. So we have English, right? We have English. 3 to the power x is 10. 3 to x is 10. We want to rephrase this English so that not only is x the subject, but is at the beginning of the sentence. So another way of saying this, x is the power to which 3 must be raised to give 10. It's the same thing, right? This sentence here is the same as this sentence here. Obviously, the second sentence is a little more words, right? But the idea is you want to make x the subject of the formula, right? You don't want it mangled up in here. So what these guys did, they say, you know, let's write it in a way where x is the subject. So x equals, x is a power, so is x is a power to which 3, which is the base, 3 must be raised to give 10. So they sat down and there's like, how we can write this boy? We can write power 310. They might think there's 3 raised to the power 10. So we can use power. We can use index or exponent, because these words, you know, conjure up feelings that is a power being raised, right? We want to rephrase the question, but we need a new terminology. So we can use power. We can use IN because you think is an index, which is another thing in mathematics, or integration, which we're going to do next. So we can use that. We can use exponent because there's a notation where, you know, there is a exp, like exp exponent, you know, like 2, 3. That's 8, 2 cube 8. That's 2 cube, right? So we got exp was already being used. Power is kind of the same thing. You think power 310 means 3 raised to the power 10. You had to have a different looking thing. So what they came up with is like, listen, let's put the base a little bit lower because it appears lower than the index here, right? That 3 is lower than the x in a sense. The x is higher. So I will use a different term. I will say log, right? And I'll put the base here. I'll put the base here of something, right? So I'll write it like this. So x is the power to which 3 is raised. The fact that 3 lower means 3 is the base, and 10 is the answer. So we find in the power of 10 is like a reverse thing. What must 3 be raised to give 10? That's the question you're asking, right? 3 to what power is 10? That's the question. So if I ask you, you know, 2 to what power is 16? Right? You'll say, well, 4. 2 to the power 4 is 16. But 3 to some power is 10. Like, what's that? So I need the two things how to be together. Just like the English, the 3 and the 10 how to be together in words because x is the subject. And we want to say x equals something, right? We want it to be a base, not a power. Right? So I don't like this form here. This form looks confusing. But both of them say the same thing. Huh? Both these equations say the same thing. So a synonym for a power or index or exponent is a logarithm. It's just a synonym. A logarithm is an exponent, is an index, is a power. But the context in which you use this is very different. When somebody asks you, oh, what is a logarithm, they need to give you two things. What you're finding a logarithm for and what base you're dealing with. Because you can't just ask me, what is the power? Right? You can't just say, oh, what is the logarithm at 10? That's an incomplete sentence. Right? Logarithm of 10 with respect to what? A logarithm is a power. Something is being raised to a power to give 10. What's the something you're dealing with? Is it 2? Is it 5? Is it 10? Is it 100? If I don't know what the something is, it makes no sense. So when you're asking somebody, hey, what's the logarithm? You need to give them two pieces of information. Somebody said, well, what's the logarithm of 5? I was like, what? That makes no sense. A logarithm is a power. If you're asking me what's the log of 5, you're asking me there's something raised to some power, the logarithm, to give 5. What is the context you're dealing with? What's the base? Right? So the base is written after the word log and a little bit lower. It's like a subscript. Okay? And you're asking me what power 3 has to be raised to give 10. I don't know what this answer is, but I know it's more than 2 because 3 squared is 9 and 10 is a little bit bigger than 9. So I expect this answer to be 2 point something. Now it can't be 3 either because 3 to the power 3 is 27. So it's somewhere between 2 and 3, this answer is, and it's very, very close to 2. More closer to 2 than it's closer to 3, the answer X. So, this answer, I know, 2 I know this answer is something like this. I know whatever this answer is, it had to be between 2 and 3, because 3 to the power 2 is 9 and 3 to the power 3 is 27, and 10 is between 9 and 27. Okay, I'm not sure what this is. So for, we have some examples here, right? Ugh. So somebody asks you, they say, find, find so that say find log 2 of 8. What does that mean? Log 2 of 8. So first of all, you see log, which means logarithm. So they're asking you for a power. From the notation that they use, what is the base? The base is 2. So they're asking you for the logarithm of 8 to base 2. So 2 to some power is 8, and they want to know what that power is. That's basically what they're asking you there. Right? That's how you read it, which is what Dean found on Google, right? I'll use that example just now, right? But that's what this is. What power must 2 be raised to give 8? That's what they're asking. Right? What power must 2 be raised to in order to get 8? Well, everybody know the answer is 3, right? 2 cubed is 8. So, I could say, well, let x equals let x be that. How do you rearrange this equation to exponent form? What's the exponential form of this? The exponential form is your ID base, which is 2, your ID power, which is the logarithm, so 2 to the power x, and that's equal to 8. So, back and forth, this is called a logarithmic form of the equation, right? I'm gonna write that here. It's called a logarithmic form. This is very different from the exponential form. I'm gonna bold and underline this thing. So you have an exponential form and a logarithmic form. They both say the same thing, but they say it differently. Right? Look, both forms here. First one is the logarithmic form. The second one is the exponential form. So you just had to get used to it, essentially, right? To see in the logarithmic form in your mind. Right? So try our next one. So example 2. So was the logarithm of 100 to base 10 with respect to base 10? Right? You're asking for a logarithm. So what power must 10 be raised in order to get 100? That's what they're asking. 10 to what power is 100? Anybody? The thing with logarithms is you can't really understand this topic unless you're fairly competent in indices, right? So you have to know your indices, right? So you could say let x equals 10, and therefore if you change it in your mind, you're doing this, so you wouldn't write this out in an exam or a question. You wouldn't write this up, but you're doing this in your head. It's like log 10 over 100. 10 is the base, so he's asking me what is the power that I have to raise 10 in order to get 100. That's not so bad. You know? Not so bad. What do you think is log 5, 1? Log 5 of 1. What is the logarithm of 1 with respect to base 5? So you're asking me what power must 5 is the base. What the other is 5 to in order to get 1? Anybody? Tell me that. Think back at your laws and indices. So if I have log 5 of 1, rearranging this here, 5 to some power x is 1, right? We know the only thing that could be possible is 0, right? 5 to the 0. Does it matter what the base is here? Log 5 or 1. Would the answer change if the base was 7? Does the base matter here? If you ask what is the logarithm of 1? Base don't matter, right? For any non-zero base, okay, logarithm of 1 is always 0. So I could actually say, you know, So for all non-zero x, no matter what the base is, once it's not zero, log of 1 is 0. Okay, this makes sense to you all because you ask him here, if I have a base x and it's not 0, what power must it be raised to give 1? And the idea is 0. Okay, try some more. So what is a logarithm of 1 over 49 to base 7? This one might be a little tricky, but yeah, listen, 7 has to be raised to some power to get 1 over 49. What would that be? Anybody? Seven to some power is 1 over 49. What's 1 over 49? 1 over 49 is 49 is 7 times 7. Right? That's 1 over 7 squared. That's 7 to the power. No, not a half. 7 to the power half is the square root of 7. Square root of 7 is not 1 over 49. Square root of 7 is a irrational number. You can't represent that as a fraction. So the answer is -2. This is what I said before. Your indices, your laws of indices, how to be good. You remember your indices. Right? So logarithms could be negative, right? Logarithms could be 0 and logarithms could be positive, right? So the logarithmic function is a smooth curve, right? You could check out Desmos to see it if you want. Let's see how it looks. So you could plot a graph y equals, where's my function listed? Functions. So you have a bunch of functions here. Log of what? Say log 2. As a constant. Hold on. Statistics, this distributions. It is like using it as a calculator, right? So it was log of x, right? So you see how is a smooth curve here, right? It dangerously close to that y-axis when x is very small and negative. Sorry, when x is very small but close to 0. And that's because the closer to 0 you get, the power, remember, is a fraction, and that the y value gets dangerously large. Okay, so passes through the point 1, 0, right? Because when you want to find a logarithm of 1, the power is always 0. That would give the value 1. That's what we said here, right? For all x, log x of 1 is 0. So let's see some functions here. Y equals ln x. This is log to base e. The first one is most likely when you just see log, usually the base is 10. When you see ln, the base is e, second most important number in mathematics. And sometimes when you see, I don't know if they have it here, lg of x. I don't think they have it here, lg, right? Usually in books, when you see lg of x, they mean the base is 2, right? So I have certain popular abbreviations for right? So you could do like log 5x. This is log 3 of x. Y equals log 7 of x. You notice all of them, all I'm passing through this common point here, 1, right? That's because of this rule here. It don't matter what the base is once it's non-zero. Log of 1 is always 0. So when x is 1, the value is 0. So you're seeing it here. This is log 5x, log 3x, log 7x. These are different logarithmic functions, but different bases, right? The general shape of the curve is the same for all of them. That's what I'm trying to show you. General shape is the same. They all pass through that point there, 1, 0, and they just get bigger or smaller as the case may be. When we started calculus in lecture 10, we had some derivative functions here like sine, cosine, e, right? E is the natural number, the exponential function, the natural exponential function, e to the ax. E is a constant. This ln, ln x, that is log to base e. Okay, it's a very, very important function in mathematics. At least you ought to know for this course, because if you look at your outline, we talk about here ln x, log to base e, right? And e to the exponent, the natural exponential function, e to some power. E is a special number in mathematics, 2.718 something like that, right? You see it on your calculator if you have a scientific calculator. See E here, close to pi. So I press E, see 2.718. If you press pi, you get pi. These numbers are related to each other and they appear all over mathematics, advanced mathematics. In places you never thought you would have seen them appear, they appear. Both e and pi. Those are the two most important numbers in all of mathematics. So they're asking you to know what ln x, lnx is log to base e, right? lnx. And as most we could see it here, could get rid of all of these guys and say y equals ln x. Okay, same shape as the other logarithmic functions, basically. Passes through 1, 0. The derivative of that function is 1 over x, right? This is what logarithmic differentiation is about. And we saw it here, differential ln ax is 1 over x still. Doesn't matter what a is, it's always 1 over x, right? All right, so we have some proofs here, these things to show you that is not magic, right? If I say p is equal a to the power m, if I read this is exponential form, if I write this in logarithmic form, m is the power, m is the logarithm to which base a must be raised to give p, okay? So what I'm doing, I'm changing it from the logarithmic, from the exponential form to the logarithmic form. This is an exponential equation here, q equals a to the power n. The logarithmic form of this is log of the base to the answer. That's what the power is. Okay, so these two things shouldn't be too difficult to understand why I did that. If I multiply p by q, that is a to the m by a to the n, which from your lower indices is a to the power m plus n. We add the indices, right? We add the indices. Now from this equation here, if pq is a to some power m plus n, then m plus n is the logarithm of a to pq, okay? M plus n is the power to which a must be raised to give pq, right? So m plus n is the power to which a must be raised to give pq. But m and n are log a of p and log a of q from above here. So we see that the logarithm of a product is a sum of the logs once the base is the same, right? Similarly with division, if you divide am by a to the n, you just subtract the indices. But if you look at this equation here and you write it in logarithmic form, m minus n is a logarithm, and that is the power to which a must be raised as the base to give p over q. But m minus n from up here is log a of p minus or log a of q. So when we have a logarithm of a fraction, that means we subtract in logarithms. The same base, of course. And then p to the power n, what is p? P is am to the power n. We multiply the indices, am, n. If you watch this equation here and you write it in logarithmic form, the logarithm of p to the n, right, to base a is mn. Mn is the logarithm. So mn is the power that a has to be raised to give p to the n. That's why I write it in this logarithmic form here. And then m by n, that's n by m. Remember, m is log a of p. Okay. So the logarithm of something raised to a power, we just put the power on the outside. So this is normally used to simplify questions. And we could do some examples with that now. So we have this question here, find log 4 of 9 plus log 4 of 21 minus log 4 of 7. Each one of these individual things is kind of terrible because what power must 4 be raised to give 9? You know, that's not a nice number. 9 is not a power, a straightforward power of 4. Similarly, 21 is not a straightforward power of 4, neither is 7. But you could use the laws of indices, sorry, the laws of logarithms up here to simplify this, right? So if you're adding logarithms, log 4 9 plus log 4 21, from this rule up here, if you're adding logarithms, P and Q, you just multiply them. And if you're subtracting logarithms, you divide them, okay? So I could say, I could work this out in pieces. So I'll rewrite the question. I'll just put brackets around it to show you the parts I'm working out first, right? So I'm gonna work out this part first. Now this is just 9 by 21. Right? So that is, we multiply PQ. When you're adding logs to the same base, P and Q, you're adding them, you multiply that. So log 9 plus 9, log 21 is log 9 by 20. 9 by 21 is what? That's 189.
189.
Thanks. So that's 189. And now we subtracting logs. So subtracting logs means divide. You say log A of P minus log A of Q. You just log A and you say P divided by Q. Right? So this here is log of a fraction. Now 189 over 7, that is 27, I think, right? Because this 189 is 9 over 21. And if you divide that by 7, 7 going to 21, 3, 9 3s are 27. So this is log 4 of 27. 27 is actually 3 to the power 3, okay? And we saw that the log of P to some power, you take the power and you write it in front and you just log A of P. So this 3 could come in front here. So this is 3 by log 4 of 3. That's the simple answer. Right? This is a better way of writing the answer than log 4 27, because 24 is something to a power. Right? Hope this kind of made sense, how to use the rules. And the rules are documented here. You see here, when you do logarithmic differentiation, these are the 3 rules here. Log A by B is log A plus log B. If you're subtracting logarithms, you have to divide. And if you're log A to some power n, you put the n in front of the log A. That's those 3 rules I was talking about here. So this should answer the question of what is a logarithm And what is this lnx that we talk about when we differentiate? And right, this ln x here that you all see, that your syllabus insists that you all have to know about. Lnx, log to base e. That is just normal logarithms. The base is just the number e instead of like 2 or 3 or 5 or 10 as the case may be. So chapter 13 in the textbook is logarithms, and you could try some of the problems here, right? Natural logarithms is abbreviated. Instead of writing log to base e, they write it as ln. Okay, and you could use a calculator to find out. The next chapter has natural logarithms. But these are the rules that I just showed you all. There's no magic, there's actually a proof of them. And they ask you to evaluate some of these things here. Logarithms are very useful and more advanced work. We're not going to do a lot of it in this course, but you could kind of just go through this and make sure you understand the concept of the logarithm function. It's not like powers or roots or anything like that. Logarithm is an inverse operation. As if you see here, if you plot the graph y equals e to the x, you see these curves are the reflections of each other, and the reflections in the line y equals x, right? So both curves, if you reflect any curve in the line y equals x, you get the other curve, right? So ln x and e to the x, they're inverses of each other, the reflections of each other in a sense, right? Not inverses, reflections. You could look at some of these examples here in the book and some of the answers to see how they do it. Usually use logs to solve equations where the unknown is a power, right? But we're not going to really be using these kinds of things in your assignment or in this course, but you should probably just understand what a logarithm is, right? And what an exponential function is. This is a natural exponential function, or e to the x. E again is that number that we saw earlier. If you press E here, is 2.71828. It's a irrational number. It cannot be expressed as a fraction. But just like how you have e to the, you have, look, e to the x here is an exponential curve, the red curve. They're just showing you how to evaluate it. Forget the power series. We're not going to do power series. We don't do any of those advanced things in this course. Neperian logarithms is a natural logarithms to base e. These appear a lot in mathematics, especially in calculus, the non-standard functions, especially in laws of growth and decay. This is where you would normally see those functions, because natural laws in the universe, in physics and engineering, natural laws, natural systems, biological systems, economic systems, political systems, electrical systems, fluid systems, thermodynamic systems, right? All these systems have the same differential equations, more or less. And the solutions to these differential equations usually involve e, the natural number, it has an exponential function. So here we see how something could be cooling or rising up to a temperature, right? See Newton's laws of cooling. All these laws deal with that number e. E shows up a lot. So it's very, very important in mathematics with a lot of laws, the way, because look at this, this is the growth of charge on a capacitor, or the growth of a population in a biological system, right? This is decay or radioactivity, right? Or the cooling of a object in a certain room held at a certain temperature. This is how the coolant behaves. So lots of different physical phenomena obey these differential equations where the solutions is an exponential function. This is why they're so important in mathematics, right? So 13 and 14 will go into that specifically. So we finish differentiation. We want to move on to integration now. So we start from chapter 48. Right? So integral calculus, what is this about? You could, at this level, it's very useful to look at integration as the reverse process of differentiation. What was differentiation again, if you all remember? Differentiation was finding the gradient function. Given our original function f of x, there's some steps to follow and we could find a gradient function. So that way we could find the gradient of a curve at a point without drawing tangents. We just find the gradient function and plug in the x value and we know what's the value of the gradient at that point on the curve. So given the original function, what is the gradient function? That's essentially what differentiation is. Integration is the reverse, right? So given a gradient, function f of x, the original function is also a function of x most likely and is given by y equals so if we know what f prime of x is the gradient function. So to go from the gradient function to the original function now is the opposite of differentiation, which we call integration. So we use this symbol here in front of the gradient function. And we say what we integrating with respect to. We say the integral of f prime x dx. This is with respect to x. Okay. This is called the argument. X is the argument. So with respect to the argument is the original function. So you see here, if f of x is 2x squared, then f prime x is 4x. But if you're given 4x, the integral is 2x squared. Well, plus some constant. We don't know what the constant might be. So when we say integral 4x dx, it means the integral of 4x with respect to x. X being the argument. You need to specify it so that if you have other letters, they'll be taken as constants. Now, one popular thing to notice is that the integral of 4x, even though it's 2x squared, is really 2x squared plus some constant, because if you had the original function plus some number, then differentiate and it will give the same gradient function, right? So like, it don't matter what if there are constants involved, right? With differentiation here, when we do differentiation, I'll give an example. You see this 4 here. Notice when we differentiate 4, we got 0. So the original function that we differentiated may or may not have a constant. So that if we have the gradient function, like this is the gradient function here, 4x minus 3. If we go in the reverse direction and we find the original function, then we have to integrate. But when we integrate 4x minus 3 and we use rules, there may be a constant, plus or minus some number. We always have to take that into consideration. So wherever we write, we say the integral of 4x dx is 2x squared, but maybe there was some constant that was added on. Because if I differentiate 2x squared plus c, no matter what c is some number, it's not a function of x. If I differentiate 2x squared plus c, I will get back 4x. But going in the opposite direction, integrating 4x, you don't necessarily get back 2x squared. You may get 2x squared plus some constant. And this is called the arbitrary constants of integration. Okay. So we reverse the rules of differentiation to find integration. And you have these formulas here. This is the polynomial formula here. So remember differentiation, we said that, where is it? Where the other rules, boy? Right, look, I'm here. You see, if you differentiate ax to the power n, it says the first thing to do, multiply the entire function by the power n, so anx. And the second thing to do is to decrement the power. So if you apply those rules in the reverse order, that's how you undo it, right? The reverse order is increment the power by 1 and divide by a. And that's what they're doing here. Increment the power by 1 and divide by n plus 1. Sorry, not a, n plus 1, right? So if it increment n minus 1 by 1, you'll get n. And if you divide this thing by n, you'll get back the original function. Okay, so that's all this is doing here. For polynomials. Polynomials are the easiest functions you would get in all of mathematics, right? So this is the formula for the integral of a polynomial function, ax to the power n. X could be raised to any kind of integral power, right? Once the power is not a variable as well. And you always have the constant of proportionality. And you can check all these results by differentiation, right? These are some standard integrals here. We need to focus, well, I'll write down the ones we need to focus on, right? Because your syllabus says which one to focus on. So you see integral calculus of ax to the n sine cosine 1 over x and e to the ax. So let me summarize these here for you. So these are some popular integrals here, very similar to the popular derivatives. And these what you need to know based on your syllabus here, right? These functions here. So we'll do some worked examples to show you how to find the integral. And remember what the integral is. The integral of a function is another function. Right? Integral is like an operator as well, just like the first derivative, the differential operator. In differentiation, we have a function and we want to know what the gradient function is. In integration, we have the gradient function and we want to know what the original function is. It turns out that integration is a lot more difficult than differentiation. It has some fairly simple looking functions that we cannot integrate. We don't know what the original function is if the gradient function is the original function. So we'll do some examples here that we can check from the book, right? You see this question here, determine integral of 5x squared dx. So pretend 5x squared is your gradient function. What's the original function that would have caused that? That would cause this gradient function. Similarly to tk with respect to t, right? Well, the 5x squared, we use this formula here for the, I highlighted this ax to the n here. If you see my mouse moving. So we compare 5x squared, a is 5 and n is 2, right? So 5x squared, integrate 5x squared, you get 5x cubed over 3 plus c. C is whatever is some constant of integration. Some books use c, some books use k. We use in c, right? This is the capital C at the end. Similarly, integrate 2t cubed. What you do, you take the 3, which is the power, you increase it by 1, you get 4, and then you divide by that power 4. That will cancel with the 2, right? To get a half t4. And you see these examples here, integration is a linear operator, just like differentiation was a linear operator. It means integral of a sum of products is a product of sums of integrals, right? Let me see. I don't think I said that right. Here we had the linearity operator. Right? 12, we could say something like that too. So the operator is a linear operator. So if I have integral of these things with respect to x, right? So if you integrate a sum of products, right, you will get another sum of products as well. F prime x being a gradient function, but f of x is the original function. So integration is like going in the reverse direction. Right, so you see the a comes in front of the integral sign. All constants, they come in front of the integral sign. They don't really take part in the integration and the rules. Okay. F prime x with respect to x becomes f of x, and g prime x with respect to x comes g of x. So you could apply it to a sum or difference of functions like how we have here. You just do the integration one at a time. So the integral of 4, what is the integral of 4? Well, that's x to the power 0, right? So you increment the 0 by 1, and then you divide by 1, so you'll get 4x. 4x to the power 1 divided by 1. Similarly, 3 over 7 is a fraction. The integral of x is x squared over 2. So just multiply 3 by 7 and you get 3 over 14. The integral of 6x squared, you increment the 2 by 3 and then you divide by the 3. So you'll get 2x cubed. See? Plus some constant the integration. Problem 3 shows that for these type of problems, what you could do is divide by the denominator, divide each term in the numerator by the denominator, right? So you see they divide it here, and then they get 2 fractions to simplify, and then they just apply the rules. So the integral of x squared over 2 with respect to x, yeah, the 2 increment by 1 to give 3, and you divide by 3, so you get x cubed over 6. Similarly, integral of 3/4 is 3/4 x, or 3x over 4, as you see here. So there's lots of examples using the polynomials here. Essentially just using the rule. Which rule is that? That's this first rule here, the ax to the n plus 1. That's all these examples showing here. Sometimes you have to find the constant of integration, and they will have to give you some information to find that. But this here just showing you ways of applying the rules. Okay, these are the polynomial rules. They're just using different letters like theta and y and g and all these things, but it's the same thing, right? Like let's look at this one here, the integral of 3 square root of x. What's square root of x? X to the half, right? So you have a bigger than the indices with this one, right? What you do is if you integrate an x to half, you take the half, you add 1 to it, you get 3 over 2, and then you divide by that 3 over 2. So you get 3x to the power 3 over 2 divided by 3 over 2. You invert and multiply, you get 2 square root of x cubed plus c. So this topic, your indices had to be real good. Your algebra and your indices and your factorizer. Because that is a fundamental thing with calculus. Your algebra skills have to be very good. Here I have trigonometry, 4 cos 3x. That's like this example, cosine, except a is 3 and alpha is 0. There's no constant angle. So you get 1 over the a, 1 over the 3. A is 3 here. And sine, cosine changes to sine. You differentiate, if you integrate sine, you'll get a negative cosine. And you divide by the 2, as they did here. You don't have to know sec squared and cosec squared. You can disregard those things. But you need to know the exponential. These are the 2 exponential questions here. And you need to know ln. Well, not ln, the 1 over x is ln x. So see like this 1 over, this is 3/5 by 1 over x. So there's 3/5 ln x plus c. It's not going to be very difficult, really. It's just you have to take your time and apply the rules and simplify or factorize as the case may be. So try this question here, example 6. Integral of 2 by the square root of x cubed minus 3 over x squared. Okay. Integrate this with respect to x using the rules above, the polynomial rules, and simplify your answer where you could. What you have to do with this question is write it in terms of powers so that you could recognize what a and n is. Okay. So the square root of x cubed, this is, if you have to write it, then you could write it as x cubed to the power. Remember, square root is the power 1 over 2, right? And the x squared, the 3 over x squared, this is really 3 multiplied by this is really 3 by the power x to the power negative 2. Right? Remember, negative 2 is 1 over x squared. Right? Let's simplify this again. So the x cubed all to the power of multiply the indices. So this is 3 over 2. And we take out the x squared. Right? So you get 2x to the power 3 over 2 minus 3x to the power negative 2. So this is clearly you will differentiate a and n in each of the terms. So you apply the integral to both terms, right? So there we go. So the power here is 3 over 2. So you have to add 1 to 3 over 2, okay? So let's take our time with that, write it here. So the 2 and the 3 could come out. So what we could do, we could rewrite the question and take out the, you could represent it as a sum. 2 integral of this dx minus 3 integral right? So we pull out the 2. We take the 2 that was in front of the x and put it on the outside the integration sign. Similarly, the negative 3, put it on the outside the integration sign. So you have to take out this 3 here, right? So you're really only dealing with x to some power. The constant will come back in at some later point. So this is 2 by something minus 3 by something plus c. That's the answer, right? So it's just to figure out what the things are. So this 3 over 2, we add 1 to it. So this is x to the power. We say 1 plus 3 over 2, right? That's the power that x is being raised to, okay? We see it here any examples in the book here. Let me show you. You see here, negative 3 over 4. So we add 1 to the negative 3 over 4, and then we divide by the power. So this itself is a fraction, right? So 2 by something, what we do, the power 3 over 2, we raise it by 1, we keep x to that power, and then whatever that power is, 1 plus 3 over 2, we have to divide by it, okay? Similarly for the x to the minus 2 here, we say, okay, this is 3, this is a fraction, right? X to the power, we say negative 2 plus 1, right? And then that same negative 2 plus 1, we put it to the bottom here, negative 2 plus 1. I might need this left. Okay. So that's the story. Yeah, whatever the power is, you increment it by 1, and that final power you divide by it, and the constants on the outside to be multiplied. Okay, so it's just to simplify now. Now, if you notice the question stop, it's not about calculus anymore. This is an algebra question now. You have to simplify this. So you have to use your rules of fractions, factorizing, difference of two squares, simplify, and all those things, right? Calculus questions is typically finished in one line, like this line here done, applying the rule of calculus, and then you spend all that time simplifying the answer. Look at this here. Watch out this question. the calculus actually finishes here and this line here. 1, 2, and the fourth line it finishes, right? This line here. And then the rest is just simplification, right? So let's do this now. So what is 1 plus 3 over 2? That is 2 over 2 plus 3 over 2, that's 5 over 2. So this is 5 over 2 divided by 5 over 2, okay? This here, minus 2 plus 1 is negative 1. Okay? This minus 1 and this minus 3 would cancel here to give plus. So write a new line. So this minus turns to positive and x to the power minus 1. So that's a fraction of 1 over x. Right? So 3 by 1 over x. This is 1 over x here, right? Negative, negative, positive. The x to the power minus 1 is 1 over. Here now, dividing by 5 over 2 means multiplying by the inverse, multiplying by 2 over 5. So this is, instead of dividing by 5 over 2, so dividing by 5 over 2 means multiplying by 2 over 5. And the power is still x by 5 over 2. So this is 4x 5 over 2 divided by 5. So 4x to the power 5 over 2 divided by 5, and that's 3 by a third. Just take out this 3 here. And then you could write the question in terms of square roots, right? You could rewrite the question in terms of square roots. X to the power 5 over 2, that is the same as square root of x to the power 5. Right? So x to the power 5 over 2 is the square root of x5 over 5 as the denominator, right? So this looks like the actual answer here for something like this. To test your answer, if you differentiate this here, you will get back the original function, which is up here, right? Definitely this will be 3 over x squared. And this would be the 5 over 2. By this, the 5s will cancel, the 2 will cancel the 4 to give 2, and then it'll be 2 x 3 over 2. Yeah. So this is the correct answer here. So look at this example here. All right. To try this question. And you can finish it up for homework. All right. They said the curve has a stationary point at -1 on 1. They give you the coordinates of one of the stationary points. And they say the gradient function is this here, 6x squared plus ax minus 12. What I want you to do is find the nature and coordinates of all the stationary points. Okay, so they're trying to hint at you here that it have more than one stationary point. You already know this point here, but you don't know if it's a minimum or a maximum. So this is a good revision from lecture 11, where we find minimum and maximum and we classify them. We usually classify them by finding the second differential coefficient, the dv, d squared, dr, x squared. So for this question here, if you say dy dx, then it's d2y dx squared or f double prime x you want to find to classify the stationary points, right? You see here, if f double prime is more than 0, if it's more than 0, then is a minimum. If it's less than 0, is a maximum. If it's equal to 0, is usually a point of inflection, but it's good to check with the sign test, the dy dx test here, like this here. Not all the time you could do the sign test, right? So this is a good question to start. You see, it's a very short question. It's worded in essentially one line or 1.5 line, not even 2 lines, right? But there's a lot of stuff they're asking for. It's very, very simple to ask a very difficult question in calculus, okay? So think about how you would do this and start it now, and then you can finish it up for homework.